Hi, welcome to topic 3.2. This is our work video. Um, so in here, we're also going to talk about the famous work energy theorem. Again, I mean, it's just like what we've been talking about, how we're going to take the ideas that you learned in the algebra-based course and expand it. So let's talk about work. Remember, work is the amount of energy transferred into or out of a system by force exerted on that system over a distance. So a thing to remember, work done by a conservative force is path independent. So it only depends on the initial and final configurations. And then the work done by a non-conservative force is path dependent. So it depends, and it depends. It's going to be dependent on how it gets there. And so what you could see here, this little chart, right? Kind of the differences with work. So if I have a conservative force, work 1 equals work 2. For a closed path, it's going to be 0. The force is independent of the path, so it doesn't matter how you get there. Some of the conservative forces, especially the three big ones that we talk about here, really there's four. You have the gravitational force, both Fg and or F little g and F big G, so I can consider that two forces. The spring force here in mechanics, and then in E&M, you have the electrostatic force. Now, on the other side, this is where we kind of introduce in some new topics, right? So a non-conservative force. So what is that telling us? Is that the work 1 does not equal work 2. And for a closed path, it does not equal 0. And then the force will depend on how it gets there. And some of the non-conservative forces that we can contend with are going to be friction, air resistance, and tension in a cord are going to be some of those non-conservative forces. Okay, so work, much like energy, is going to be a scalar quantity, but it could be positive, negative, or 0. Remember, it's going to be dependent on how that force is acting. And so the work done by an object by a variable force is calculated as such. So the work is the integral from a to b of f of r dot dr. Okay, so again, that's going to be for a variable force. If the force is constant, it's just the old classic, right, FD cosine theta equation. So put a little caveat there, it says constant force. Okay, and how can we tell constant versus variable? One, if it's a variable force, they're going to give you the function. If it's a constant force, they're going to just give you a number for it. All right, the work energy theorem, you talked about this in an algebra-based course. It states that the change in an object's kinetic energy is equal to the sum of the work being done by all forces exerted on the object. So delta K is equal to work done. You can say it's 1/2 mv squared minus 1/2 mv initial squared equals the net force times delta X. Okay, so that is how you would write the work energy theorem. And then finally, we talked a little bit about this in an algebra-based course. Work is equal to the area under the curve of a force displacement graph. Okay. In an algebra-based course, your graphs were probably just flat lines, because then it's just a rectangle. They may have given you some triangles just to give you some variety. Here in Physics C, you're going to be given functions and actually have to apply calculus principles, right? So this is what this means. And remember, integral equals area under a curve, right? Okay. So now let's look at an example problem. Again, students are always asking for calculus examples, and trust me, this is one that has that. So we're going to derive two expressions. We're given the maximum acceleration equation, and it tells us that, we're given the acceleration equation, tells us that it's a maximum acceleration sine pi t over t, little t over big T. So little t is our variable. Big T is the time when it reaches what they're calling terminal velocity or terminal speed. Okay. Hill is inclined at an angle theta above the horizontal. The friction between the skis and the snow is negligible. Express shear terms in terms of given quantities and fundamental constants. So part A, derive an expression for the velocity of the skier as a function of time during the acceleration. Assume the skier starts from rest. Okay. So remember, we're given the acceleration equation. Okay, and what they're telling us that it's starting from rest, and remember, velocity is the integral of acceleration, right? So we have, sorry, I erased half of that there. So velocity is equal to the integral from 0 to t of a max sine pi t over t dt. Okay, and so now we do a little bit of our we do our integral. So integral of sine ax is going to be -1 over a cosine ax. Okay, that is on your formula sheet. You don't have to memorize it. So we know that our velocity as a function of time is going to be negative a max big T over pi cosine. I put theta, but it's actually going to be what's in our expression. So cosine pi t over t. Sorry, I switched colors. Okay. Now we have to evaluate that from 0 to t. Most of the time when you evaluate from 0 to a number, that 0 part will cancel out. But you have to remember cosine of 0 is not 0. Cosine of 0 is 1. And so what happens is when you substitute that in, I'm going to write it up here a little bit, you will end up with velocity equals negative a max t over pi. That's going to be constant. And we're going to have our parentheses. We're going to have cosine pi t over t. And what happens is if I want to bring that negative sign in, because that negative sign is actually from the integral component. So I'm going to change this up a little bit. You're going to end up with cosine of 0 times cosine pi t over t. And remember, this is 1. So our function for velocity is negative a max t over pi. And it should be capital T, not lowercase t. Times 1 minus cosine theta. I keep writing theta. It's going to be 1 minus pi t over t. Okay, so that is our velocity function. Now we're going to figure out the expression for work, the work done. So it's going to be work equals delta K. And we know it's going to be 1/2 mv final squared minus 1/2 mv initial squared. Well, starting from rest, that goes away. So we would have 1/2 mass times, I always like to call it the mess. So this mess okay, squared. Now what happens is when this happens when capital T, when T is equal to capital T. So in fact, I'm just going to go back here real quick and change this T to a capital T, and you'll see that we end up with 1 minus cosine pi. So we have 1/2 m negative a max t over pi times 1 minus cosine pi. Well, cosine pi is -1. So we end up with 1 minus 1 there. And I square everything there. So you end up with 1/2 mass times negative a max squared times capital T squared times 4 over pi squared. Well, that 4 and the 2, right, cancel out because it makes it a 2 up there. And so your final work equation, right, is going to be -2 a max mt squared divided by pi squared. Sorry, I lost a little room there. But that is going to be our work done by this rope pulling the skier up the hill. All right, so in the next video, we're going to talk about potential energy, and we're going to introduce in a little bit more calculus here, because in algebra-based course, you're given potential energy equations. Here in a calculus-based course, you're given the function.